In Yellowstone National Park, geologists say one of the park's famous geyser basins now has a new hot spring. Scientists say this new thermal feature popped up in Norris Geyser Basin recently.
Yellowstone National Park is pulsing with motion. In recent days, park officials have reported hundreds of small earthquakes rippling through the volcanic region, and the swarm has drawn intense attention from scientists and the public. These tremors are mostly tiny, too small to knock a picture off a wall, but their number and clustering make them meaningful. Each tiny quake is a signal that the planet beneath Yellowstone is active, shifting, and in the process of changing in ways researchers want to understand. For experts, the swarm is a rare chance to watch the hidden plumbing of a famous volcanic area in real time. Yellowstone sits atop a powerful geologic hotspot. The park's famous geysers, steaming pools, and colorful mineral terraces all exist because heat from deep in the earth warms water and drives it toward the surface. That heat comes from a zone of magma and partially molten rock miles below. Over long stretches of time, the movement of that heat and the pressure it creates warp the crust. The surface may look calm and beautiful, but underneath, there is a restless world of rock, water, and gas that twists and shifts as pressures change. Seismic swarms like the current one occur when many small quakes happen in a short time. They are not necessarily a sign of imminent disaster. Rather, they are a chance to study how stress moves through the crust. Swarms can be caused by different processes: fluids shifting through fractures, hydrothermal pressure changing as hot water moves, or magma nudging into new spaces. The pattern, depth, and timing of the quakes help scientists decide which factors are at work. In this case, the events span a range of depths and locations, suggesting a complex mix of forces moving beneath the park. To track this kind of activity, Yellowstone has one of the most advanced monitoring networks in the world. Seismometers detect the faintest tremors. GPS stations measure ground movement in millimeters. Thermal sensors monitor temperatures around hot springs and fumaroles. These tools feed continuous streams of data to research teams who can then map where quakes occur and how the ground shifts over time. The data are essential. Without them, scientists would be reduced to guesswork. Instead, they can trace changes precisely and test theories about what drives the swarm. Recent advances in data analysis are revealing more than past generations could see. New algorithms and improved seismic catalogs can find events that were previously invisible. Machine learning helps separate quake signals from background noise, unveiling rich details of swarm behavior. With these tools, experts can watch a swarm evolve hour by hour, observing whether epicenters move, whether quake depths change, and whether ground deformation accompanies the tremors. That level of detail is changing how scientists interpret seismic episodes in volcanic areas. On the surface, the park looks much the same as ever. Geysers still erupt on schedule, bison and elk graze in valleys, and tourists walk boardwalks to view thermal pools and springs. Most swarms pass without changing that surface life. However, the activity is a reminder that Yellowstone is not a static monument. It is a dynamic landscape shaped by forces that operate on vastly different timescales. Rangers and park managers emphasize safety and steady communication, making sure the public gets clear, measured updates rather than alarmist headlines. Scientists study swarms to learn how the park's subterranean plumbing functions. Earthquakes can open tiny fractures or change pressure pathways, which in turn can alter where hot water flows or how geysers behave. In some cases, changes in hydrothermal circulation follow a swarm, producing measurable shifts in spring temperature or chemistry. Most of the time, these effects are small and temporary, but monitoring teams watch thermal features closely for signs of persistent change. Any lasting shift in geyser timing or spring chemistry would prompt more focused study. Interpreting a swarm is careful work. One quake on its own is a single data point. Hundreds of quakes create a data set that researchers must analyze for trends. Are epicenters migrating in a particular direction? Are deeper events becoming shallower, which could indicate magma movement? Is ground deformation visible on GPS stations? Scientists compare current readings with long records from earlier swarms to identify what is new and what fits normal behavior. That historical context is vital. Yellowstone's past activity provides the background needed to judge whether present signals are routine or unusual. The origin of the most recent quakes likely lies in the complex interaction of brittle rock, hot fluids, and partially molten material below. Unlike a textbook volcano with a single large magma chamber, Yellowstone's magma system is a patchwork of hot zones, crystal-rich mush, and fluid pathways. Movement within this zone may not always produce dramatic signatures. Sometimes stress is relieved in many small slips along fractures, producing the cluster of tiny quakes recorded in a swarm. That mosaic nature makes each event a piece of a larger puzzle. The swarm also prompts reflection on how the scientific community communicates risk. Sensational headlines can stoke fear, but measured updates grounded in data reduce confusion. Scientists aim to explain uncertainties clearly, that a swarm itself is not proof of an eruption, that most such events do not lead to surface hazards, and that monitoring remains steady. Open, frequent communication helps the public understand what the data mean and why experts focus on careful analysis rather than alarms. Indigenous peoples long observed Yellowstone as a living landscape and held deep knowledge of its springs and changes. Today, modern scientific monitoring and traditional observation can complement one another. Local perspectives add historical context that enriches scientific interpretation, and including indigenous voices in discussions broadens understanding. This combined approach honors the cultural and natural significance of Yellowstone while strengthening the overall picture of what is happening. The global scientific community watches Yellowstone because its lessons apply elsewhere. Research here improves models of fluid flow, fault interaction, and how energy moves through complex crust. Swarm data help refine hazard assessments not just locally, but for volcanic and hydrothermal systems worldwide. Each tiny quake is a natural experiment that teaches researchers about processes that are otherwise hidden far below the surface. From a management standpoint, preparedness and planning matter. Park officials work with federal agencies and researchers to ensure monitoring is robust and to review safety plans. For visitors, the most immediate hazards remain thermal features and wildlife encounters. Those risks are more likely to cause harm than these tiny quakes. Rangers remind people to stay on boardwalks, keep distance from animals, and follow closures. Emergency teams have plans ready if surface activity shifts in ways that could affect safety. But most swarms require monitoring and study rather than immediate action. The data from this swarm will be analyzed for years. Seismograms, GPS records, and thermal readings are archived so scientists can trace the sequence of events in fine detail. Researchers will apply advanced detection methods to build an even richer catalog of microquakes, helping them see patterns that older datasets missed. Field studies may sample spring chemistry for subtle shifts, providing further evidence of changes below. Over time, these layers of information will sharpen understanding of how Yellowstone's deep systems behave. Context matters because it prevents misreading the meaning of a swarm. Yellowstone's long record includes many swarms that did not lead to eruptive or damaging activity. The scientific challenge is to identify which, if any, sequences carry warning signs and which are benign adjustments. That task demands careful analysis of multiple signals, quake location and depth, ground deformation, and changes in thermal features. No single measurement offers a definitive answer. Together, they form a picture that can guide decisions and public messages. Scientists also study the physical properties of the rocks and fluids that shape swarm behavior. Different rock types respond to stress in different ways. Porous zones allow fluids to migrate, while rigid zones transfer stress along faults. By mapping how quakes propagate through these materials, researchers can infer where fluids are moving or where fractures are opening. These insights help build models that simulate potential responses to future stresses, improving prediction tools and hazard assessments. The swarm is a reminder of the planet's active nature. The Earth reshapes itself in tiny steps and slow motions, as well as in dramatic events. Yellowstone's surface beauty masks a deeper conversation between molten rock, brittle crust, and pressurized water. Every tiny earthquake is a pulse in that ongoing dialogue. For scientists, each pulse matters and deserves careful attention. For the public, the story is both humbling and fascinating. Witnessing a place where the ground quietly rearranges beneath iconic landscapes can change how people experience nature. The knowledge that Yellowstone is alive with motion adds meaning to the sight of erupting geysers and steaming pools. It is a chance to appreciate that the planet beneath one's feet is dynamic and to recognize the value of careful scientific observation. Researchers are also mindful of common misunderstandings that can spiral into panic. Yellowstone is often linked in popular culture with a so-called supervolcano that could produce catastrophic eruptions. That image is misleading and unhelpful. Large caldera-forming eruptions did happen in Yellowstone's distant past over very long timescales, but modern monitoring and science show there is no evidence that the current swarm signals a return to that kind of event. The odds of a major eruption right now remain vanishingly small. The present activity is best seen as part of the park's ongoing complex behavior. The swarm also highlights the importance of international and cross-disciplinary cooperation. Earth scientists around the world share methods and results, comparing data from Yellowstone with observations in places like Iceland and Japan. Laboratory experiments, numerical models, and field studies complement instrument records, each contributing pieces to a larger puzzle. Graduate students and early career researchers gain unique opportunities to work on real-time data, building tools that will improve monitoring everywhere. Communities near the park benefit from this work too. Local emergency managers use scientific findings to update response plans and to tailor information for residents and businesses. Schools and visitor centers run programs that explain why the ground moves and what steps people can take to stay safe. In this way, the swarm becomes not just a scientific event, but a civic moment that strengthens preparedness, improves public understanding, and fosters respect for a landscape whose quiet beauty masks deep activity. The physical record scientists assemble from this episode will inform research for years to come. Seismic catalogs built now will help refine models of how energy moves through Yellowstone's crust. Geodetic records may reveal subtle ground changes that point to shifts in pressure. Water chemistry samples can show whether deeper fluids are migrating. Together, these data sets make it possible to test hypotheses and to improve forecasts for different kinds of unrest. Clear communication between agencies, the media, and the public matters as much as the science itself. Open, evidence-based updates reduce confusion and curb sensationalism. That means sharing what is known, what remains uncertain, and what steps authorities are taking to watch the situation closely. Measured coverage helps people stay informed without spreading fear, while allowing scientists to do the patient work needed to interpret the swarm. For now, the hundreds of recent quakes are a vivid episode in Yellowstone's long natural story. They show movement, not catastrophe, activity that will be studied, discussed, and placed into context by experts. Park staff will continue to monitor the data. Scientists will analyze the patterns, and updates will appear as new findings emerge. The ground beneath Yellowstone has spoken in many small notes. The scientific community is listening closely to each one. Scientists remain watchful and studying closely. If you enjoyed this video, don't forget to give it a like, share it with your friends, and hit that subscribe button. Your support means the world and helps us bring you even more amazing content. And hey, don't forget to turn on the notification bell so you never miss an update.